Good evening, everyone. I'm Lucas, and I'm a PhD student at University of Campinas, Brazil. I'll be the speaker for the work we've been conducting in the past few months, named MinMax-CAM, Improving Focus of CAM-based Visualization Techniques and Multi-Label Problems. These are the topics of my presentation, which is structured similarly to the article. I'll start by introducing our problem. In the last decade, multiple sectors of our society have adopted machine learning techniques as a viable solution strategy for their problems. As they are integrated to the core business decision processes, it becomes paramount to analyze, understand, and validate the information provided by machine learning models. These will be frequently submitted to an audition and validation process in which their integrity is evaluated. This naturally pushes the scientific and technological community towards the development of interpretable and explainable models. In this vein, multiple ad hoc AI explaining methods have been developed in the recent years, many of which focus on multi-class classification problems. Here's a timeline containing many of these methods and techniques. I'll further specify a few of these. So the first one, commonly referred to as the gradient backprop saliency method, consists of finding the gradient of an observed output unit of the network with respect to the input data. If the input is an image, we can represent the signal found as an explaining map, which highlights regions that contribute to the decision process of the model. As you can see in these examples, this method is quite successful at localizing and defining the overall shape of salient objects. However, it has the major drawback of being insensitive to the explained class. So for example, we ask which features contribute to the classification of the dog, and the saliency map also activates over the cat, which is not the same output classification unit, nor concept. Another very popular visual explaining method is class activation mapping. CAM produces visualization maps conditioned to the specific output by combining the positional activation signal advent from the last convolutional layer in the model, weighted by their respective contributions to that same output. CAM can be generalized to more complicated networks. For example, a convolutional network attached to a Q&A mechanism by replacing the weights by the gradient information. So here are a few examples. We can clearly see that it's not so accurate in describing the object's shapes, but it does highlight the correct objects. Another explaining method worth mentioning is the GradCam++, which normalizes the positional activation signal in order to obtain similar highlighting over all instances of the label of interest. We can see that it works very well for the VGG16 architecture, but it doesn't seem to work as well for newer architectures such as the efficient map. It is also not as class dependent as CAM, oftentimes highlighting objects of different labels. This work is also important for proposing two metrics that have been frequently used in literature. The first one, average drop, tries to capture the decreasing confidence of a model when it's fed with the input image masked by the explaining map. If the drop is low, then the map effectively highlights regions that are important to the classification of the label of interest. The second one is the increasing confidence, which measures scenarios in which removing the background has a positive impact in the classification confidence of the label of interest. If the increase is high, then the explaining map has effectively removed the noisy background patterns. The last technique I'll detail is CoreCam. It is defined as the weighted combination of the positional signals AK bounded by factor C of AK, which represent the retained classification confidence when masking the input image by each individual activation signal. As you can see, this method is quite accurate. However, it is also very slow, as computing each explaining map for a single sample requires K feed-forward operations, where K is the number of the activation signals in the last convolutional layer. The current explaining methods are very good in what they propose to do, but a few drawbacks become apparent in multi-label scenarios. Some of these are here. The CAMs overflow the region delineated by the boundaries of the objects. Large objects are not completely covered by the activation maps. Common objects from the background are highlighted with the object of interest. Some arbitrary sections in the background are often highlighted as well. And finally, objects of different labels that often co-occur are highlighted together. We draw two research hypotheses from this. The first one is that the visualization maps produced by existing AI explaining techniques do not account for complex scenarios containing multiple coexisting labels. We then question whether these co-occurrence information can be used to further refine the visualization maps. Our second hypothesis is that visual activation and unexpected artifacts in the visualization maps are created due to the classification bias acquired from strong correlation among labels present in the dataset. So, can we guide the training procedure towards solutions that favor concrete visual evidence over label correlation information? So on to the first question. We propose MinMax-CAM. The intuition behind it is to produce focus, class-specific explaining maps by maximizing the score of a label of interest C while minimizing the score of the remaining adjacent labels. The definition is similar to the one of GradCAM, but we consider the gradient of the gain function GC with respect to the positional activation signal instead. In here, the objective function JC is optimized for large score values of the label of interest C and small values for the remaining ones. You can see a TensorFlow implementation on the right, which leverages masking to prevent non-occurring labels from being added to the objective function. And because JC is a linear function and the gradient of the sum is the sum of the gradients, we can reduce it to its CAM form if we are using a model that is a simple convolutional network. Here are our few examples, illustrated through maps overlays. A few more examples, this time illustrated through their activation masks. You can see that it's doing what it's supposed to. The map for the car is avoiding the pedestrians, and the map for the people is avoiding the table, and so on. But the problem of the residual activation in the background is still present and even more prominent in some instances. And the reason why that happens is because some of these classifiers have negative weights. When they're subtracted, they become positive and highlight sections that negatively contribute to the classification of adjacent labels. In order to circumvent this artifact, we decided to decompose the min-max equation in three components: the positive contribution towards the label of interest, the positive contribution towards the adjacent labels, and the overall negative contributions, which oftentimes coincide with background regions in our tests. Of course, we can trivially reduce it to the CAM form. Our experimental setup is the following. We ran two test batteries. The first one, we considered the Pascal VOC 2007 dataset in accordance with previous work in literature and varied the architecture to inspect the behavior of each explaining method. We then freeze the architecture to ResNet 101 and evaluate the multiple explaining methods over distinct datasets in order to account for multiple scenarios and trainings. We consider the following metrics. The increase in confidence and average drop metrics are merely extensions of the ones defined by Chatoupathy et al. In the multi-label case, and they attempt to measure the explaining maps of all detected labels. We also propose the average retention metric, which measures the decrease in confidence for class C if the input is matched with the complement of the explaining map for C. We expect methods that cover most sections of large objects to have high average retention. We also propose the average drop of others and average retention of others metrics. The first one measures if the explaining map for class C is also retaining discriminative features for the other classes. We expect accurate explaining methods to have a high average drop of others. Finally, the average retention of others metric attempts to measure if the complement of the explaining map for class C covers all objects of the adjacent classes. In other words, we expect accurate explaining methods to have a low average retention of others. And we understand that it's quite difficult to analyze data and make decisions over so many metrics, so we opted to combine and reduce those. We consider the harmonic mean of the average drop and average retention of others. We will later refer to this metric as the F1 minus score. Similarly, we consider the harmonic mean of the average retention and average drop of others metrics. We will later refer to this one as the F1 plus score. Here are illustrative results for the MinMax-CAM. We can see that its direct version can accurately point out the location of objects of interest while avoiding objects of adjacent labels. For example, the visualization map for the label person highlights the bikers while avoiding their bikes, and the sofa is highlighted avoiding the person laid on it. We can also see that it's effective in reducing the residual activation previously observed over background regions of the images. These are the quantitative results for the first test battery. They seem a little sparse, but a few observations can be made here. Firstly, GradCam++ and ScoreCam result in the largest observed values for the metrics increasing confidence and average drop. This is expected as these methods tend to activate over large sections of images. When considering the F1- score, MinMax-CAM and DMinMax-CAM show much better score results than CAM and GradCam++, which indicates that they are better at erasing regions containing objects of adjacent labels while still focusing on determined regions for the label of interest. Moreover, ScoreCam achieves the best result for the ResNet 101 architecture, but it's closely followed by DMinMax-CAM. CAM and MinMax-CAM present very close results in F1+ score, closely followed by DMinMax-CAM, while GradCam++ and ScoreCam techniques produce lower score for this metric. This indicates that CAM, MinMax-CAM, and DMinMax-CAM are more successful at covering large portions of objects of label C without spreading over objects of adjacent labels. Here are the results for multiple distinct datasets. The overall trends seem more regular than the ones seen in the previous table, but they paint a similar image. Once again, ScoreCam consistently present the best values for increasing confidence and average drop. Directed MinMax-CAM is more accurate, resulting in the best F1- score for 3 out of 4 tests. And CAM and MinMax-CAM result in best values for the F1+ score. Now on to limitations. MinMax-CAM is, by construction, the subtraction of contributions, and we work under the assumption that weights being subtracted are associated with different parts of the spatial signal AK. This assumption does not hold when the network has not learned sufficiently discriminative patterns for both labels, which can be caused by an unbalanced set or a subset of frequently co-occurring labels. In such scenarios, MinMax-CAM could degenerate the explanation map. Here's an example where the explaining map for a label chair is shifted to an invalid position, which takes us to our second approach to regularized training. The intuition behind it is quite simple. As I've mentioned before, multi-label problems contain strongly correlated subgroups of labels. For example, 79% of the horses in the VOC 2012 dataset are shown next to a person. These occurrences could be picked by the model, which could learn correlational inference rules. For instance, if we'd see visual cues for a chair, then a table should probably be detected as well. Or if you see an airplane in an image, we should probably not detect cats, as they never appear together. While these rules might be aligned with the overall trends in the training set, it doesn't comprise a decision process that relies on concrete visual evidence, and they might create blind spots when the contextual information does not quite match. We can clearly see this happening when histogramming the weights of each classifier in the last layer, where quite a few kernels have a negative impact when classifying objects of a given label. And we observe a strong correlation between the weights of some of these classifiers, indicating that they rely on the same visual patterns to decide upon distinct concepts. Another way to see this is using a Sankey chart, which shows that some of these classifiers are strongly dependent on the same kernels and patterns. To address this problem, we propose the kernel usage regularization. The idea behind it is that if a visual cue is very important to the classification of a certain label C, then that same pattern should not contribute to the classification of the other labels. In other words, the occurrence of a dining table should not contribute to the classification of a chair. We also want to penalize the creation of strong negative synaptic values, so we focus on creating rules that directly associate the perception of some visual cue to the classification of a certain label. In other words, we don't create rules that classify labels based on the absence of certain objects. So let W be the weight matrix for the last classifying layer. Then the column vector WC is the weight vector for the classifier of label C, and the row vector WK is the contribution of the kernel K for the classification of each label in the dataset. If we were to apply the softmax function over WK, then the result would always be positive and quickly saturating over large values, which means strong negative synaptic values would tend to 0. At the same time, very large values would tend to 1 and quickly push the adjacent synaptic values towards 0, rendering the visual pattern invisible to the remaining classifiers. So we define kernel usage regularization as the Hadamard product between the weight matrix and the softmax of itself. We employ a common trick of subtracting each row by the maximum value to increase numerical stability, which does not affect the result. So here are a few results. This presentation is made available, and you can check these in more detail at a later time if you want. The important thing to notice here is that CAM and MinMax-CAM started to produce much more similar maps. Image A illustrates that same pathological example shown before, while image B shows the same exact sample, but using the regularized model. So subtracting the contributions for the label TV monitor no longer shifts the highlighting of a chair, it stays on top of it, which indicates that these are now separate concepts, each of which being asserted by its own set of visual cues. And these are the results. They follow a similar trend from the previous ones. The direct version of MinMax-CAM is more accurate in most of the tests, while ScoreCAM covers more section of the images. MinMax-CAM offers a compromise between them. These are the classification rules for unregularized and regularized models, which indicate that the regularization strategy does not degrade the effectiveness of the model. In fact, it has had a positive impact in most of the tests. Here is an illustration on what happens in the last classification layer. We can see that before regularization, most of the weights assumed a normal distribution, whereas after regularized, they were mostly pushed towards zero with a few large numbers. We can also observe that the correlation between the weights of the classifiers in the problem is much smaller now, indicating that they are using different patterns in their decision process. And almost all of the kernels are being used by a single classifier at most. Here are the results for the COCO dataset, and they illustrate a similar behavior. So our conclusions. In this work, we analyzed multiple visualization methods and techniques over multi-label scenarios. We generalized existing metrics and proposed new ones to account for multiple labels within a single sample. We proposed MinMax-CAM, which takes into account multiple labels within a single scenario to devise its explaining map. Our empirical results suggest that MinMax-CAM produced more focused and accurate explaining maps at the cost of not highlighting all regions of large objects. Finally, we propose a regularization strategy which favors the creation of positive and sparse synaptic connections in the classification layer, inducing cleaner visualization maps and better classification results. For future work, we intend to apply and evaluate our technique over localization and weakly supervised segmentation problems. We also expect to study ways to remove kernel redundancy by generalizing kernel usage regularization to intermediate layers. And finally, we wish to devise new ways to decouple label contextual information through knowledge distillation. These are my references, and I thank you all for your time.